So far we have discussed a lot of concepts related to turbo machinery. So how does CFD help in analyzing or designing turbo machinery? The conventional design process is based on application of empirical design methods, which are formulas, empirical standard procedures based on which we come up with a new design or rectify existing design. Design of turbo machinery involves large number of variables, and there are different design configurations which are possible, which can meet the requirement or which can bring on the efficiency or reduce the work requirement, extract the maximum amount of output. So CFD has been increasingly nowadays used in order to successfully design turbo machinery, as well as carry out analysis and validation the requirement of existing design. So there are a lot of areas where CFD comes into picture. Now, what type of analysis can be done using CFD? First is performance prediction, which means based on a design that is assumed or a historical based on historical empirical methods, if we come up with a design, we have to see what is its performance. So CFD can be used in order to virtually predict the performance of a existing design. Then there is internal flow visualization, which we can do in the form of pressure distributions that we can obtain, flow distributions inside the turbo machinery, flow path through the impellers, diffusers and other components. Using CFD we can get what is happening inside the turbo machinery without actually constructing a prototype. There is also qualitative and quantitative validation of performance, which can be done using simulations alone without doing experiment. And also we can investigate existing design. If there are any faults, if we want to rectify, we can propose some design modifications, change the CAD model of the turbo machinery, carry out CFD and see whether the changes are satisfying or not. So what is the overall process when we use CFD for turbo machinery? First we start with the initial design. After that we generate the geometry. Then we generate mesh for that particular turbo machinery CAD model. Then we input the CFD problem, we solve it using some solver, do post-processing of the results, that is extract results, and then judge whether there is optimum design or not in terms of the performance, like in terms of the head obtained, or in terms of the efficiency, the head versus flow rate curve. All these we see whether they are according to our design requirement or not, whether they satisfy the practical usage of the turbo machinery. If not, we return to change the design and repeat the whole CFD process. So this is how the CFD workflow works in terms of designing turbo machinery using CFD. So till now we have seen how CFD is applied. We also saw examples in the start, and then we saw how CFD is applied and what are the different areas in which CFD can play a role when it comes to turbo machinery or rotating machinery flows. Now in CFD, do we need anything different, or can we just apply the standard procedure or standard equations, or do we need to do anything specialized for turbo machinery flows or modeling? Well, the answer is yes. There are specific separate models or algorithms when we want to apply a CFD for turbo machinery. A concept called as moving reference frame is used. A reference frame has a motion defined relative to the stationary coordinate system. This approach transforms an unsteady flow with respect to a stationary frame into a steady flow field with respect to the moving reference frame. So inherently all turbo machinery flows are going to be or rotating machinery flows are going to be unsteady or transient, that is varying with time. All flow variables are changing with time. But this particular approach of moving reference frame transforms an unsteady or transient flow field with respect to a stationary frame into a steady flow field with respect to moving reference frame. So this is a very good conversion which we make in order to carry out turbo machinery flow analysis using CFD in a simplified manner. This approach makes it easier to specify appropriate boundary conditions, define simpler CFD problems, and also takes less time and computational efforts. So this is a usual industrial practice to use moving reference frame. Now let us see how does the moving reference frame model work. We will have an overview of that, and after this session we will go into depth of all different turbo machinery models as well within the commercial software Fluent. But first let us have an overview. So what we do in the moving reference frame model is we solve the mass, momentum, energy and equations and other quantities in the stationary reference frame. Acceleration of fluid in moving reference frame is defined using a relative velocity of the rotating frame and the stationary frame. So the next step is to define the acceleration of the fluid in the moving reference frame using relative velocity concept. The convection terms and source terms in the momentum equation are then modified of the original equation. The original momentum equation is then modified using the acceleration term, which is obtained because of the moving reference frame. So that is how the effect of rotation is included even in a steady state equations.